All right, so now we're going to finish off our discussion of resonance. There's one more piece to this puzzle that we need to learn about, and that is this idea of localized versus delocalized electrons. It's actually pretty straightforward. Localized electrons are electrons that are not in resonance, and delocalized electrons are electrons that are in resonance. Remember, resonance is all about electrons spreading out into other side-by-side p orbitals, so delocalized. Delocalization is good, we said. Remember, that means that electrons can be more spread out and there's less electron-electron repulsion. One of the reasons why it's a stabilizing effect. And we want to be able to spot when electrons are going to be delocalized. And for the most part, it's pretty straightforward, but there are one or two little tricky situations that I want to make sure that we can spot. What's essential to be a delocalized electron is to be living in p orbitals. Again, it's all about those side-by-side p orbitals and electrons being able to diffuse across them. Okay, so again, most of the time it's straightforward, but there is some tricky situations, so let me just point out one real quick. We had, taking a look at this guy here, this is the amide or the amide functional group here. We had already said that this is one example of a functional group that exhibits resonance, right? Because you have a lone pair located in the allylic position to a pi bond, right? So we can have these electrons come down, that sort of thing, right? So we already know that these functional groups exhibit resonance. So that means that this pair of electrons here is delocalized, as is this pair of electrons in this pi bond, right? These are delocalized electrons. Okay, one of the things I kind of glossed over though is hybridization. Let's take a look actually over here at this molecule. This is a primary amine. There is no resonance associated with it. Yes, it does have a lone pair, but it's not located to next to any p orbitals or anything like that. So what is the hybridization on this atom? Remember from week 1, how we figure out hybridization, we got to figure out the steric number, which is the number of lone pairs plus the number of bonds of any order. So in this case, we have a steric number equal to 4, and so this is sp3 hybridized. Okay, so now let's look over here to this nitrogen, and what is its hybridization? Well, you're really tempted to go through the same sort of process and say, okay, steric number is 4, and thus it's sp3 hybridized. But it can't be sp3 hybridized, because remember, this pair of electrons, in order to be delocalized, needs to live in a p orbital. So this is now an exception to our whole steric number rule that we learned before. Basically, delocalization is a very stabilizing force. And it can make a molecule favor an sp2 hybridization instead of an sp3 hybridization. So that's really the skill that we're going to be focusing on in this video, is being able to spot when, oh, we would have thought because of the steric number that it's sp3, but actually because of resonance, it's sp2 hybridized. And that is exactly the case here. So despite how similar these two molecules are relative to that nitrogen in terms of number of bonds and number of lone pairs, this guy here is sp2 hybridized specifically so that this pair of electrons can live in a p orbital and thus delocalize onto that carbonyl group. Okay, and so that's what you're trying to do, is if you can spot electrons that will delocalize, then you know that their hybridization has to have that empty leftover p orbital. Yeah, anyways, this is saying exactly what I just said. So let's take a look at another example here, okay? This is another example of a nitrogen that has this lone pair. And is it in resonance? Well, it follows our criteria of being in an allylic position, right? And so just like before, instead of being sp3 hybridized, which we might have thought by counting the steric number of this atom, this nitrogen is actually sp2 hybridized. So let's take a look at what that would look like, you know, considering the shape of its orbitals. So again, we have 2 pi bonds here that'll take place between these p orbitals. Another pi bond here, that's this set of p orbitals. And then again, the whole shtick here is that this nitrogen is going to sp2 hybridize so that it has a p orbital and can contribute. Which means that this pair of electrons here, you can see, is living in that p orbital. And the hydrogen is actually sticking directly out in an sp2 orbital, right? So this is now trigonal planar about that nitrogen. And then because these are all electrons that are in p orbitals that are all beautifully lined up next to one another, you could think about this as delocalizing around this whole thing. Right? And we have a tendency to think of the electrons as moving, but really they're clouds that spread themselves out into all available positions. All right, so let's take a look at this molecule here, pyridine. This is different from what we saw before. It looks very similar, but let me just give you the punchline. The punchline is that this pair of electrons on the nitrogen are localized. They are not delocalized across this ring, meaning that this resonance contributor that you see drawn here does not exist. It's not a valid resonance structure. Okay, so let's see why that is exactly. Because we would expect, you know, given what we saw before, why can't it put that pair of electrons in a p orbital in order for it to hybridize? The real reason that we're going to see is because it already has a pi bond. So let's take a look at what these electrons look like here. Right, so this molecule already had a bunch of double bonds going on. So there were already electrons living in p orbitals. So these p orbitals were bonded, these p orbitals were bonded, and the nitrogen already had a double bond going on with the carbon, which means that it already had to have a pair of electrons in a p orbital in order to spread out. A key feature, one of the, hopefully hammered it in your brain up until this point, but one thing you have to have resonance or delocalization is your p orbitals all lined up directly next to each other. And so this molecule does exhibit resonance, don't get me wrong. It's just that the lone pair is not involved because nitrogen already had a pair of electrons in those perpendicular p orbitals, which means that the lone pair in this case is housed in an sp2 orbital as opposed to a p orbital like we saw in the previous example. Okay? And again, it's because those p orbitals have to be perpendicular. So somebody might say, well, why doesn't it just sp hybridize and then it would have two p orbitals? So this is what's called a similar example. These are called Aleenes, and they do not have any resonance associated with them. And let's see why that is. In this middle carbon here, it's sp hybridized, right? Which means that it does have two p lobes that are participating in pi bonding. But remember that those p lobes, here's one here, and here's one here, are perpendicular to one another. They are not parallel. So there can't be any side-by-side overlap between these p orbitals. So there's no resonance that goes on in these Alene type molecules. Again, just trying to hammer home this idea that these p orbitals really have to be lined up right next to each other in order for the electrons to delocalize across them. Okay? So that's about does it. That's it for resonance. So now hopefully you can spot delocalized and localized electrons and be able to figure out what the hybridization is on all atoms that are undergoing resonance. Okay?